it is topical that we are looking at transient conduction where things change with time, okay, as with any other situation in life. So in fact this is beautiful. Yesterday we saw the one dimensional unsteady conduction. We can have 3 regimes. In the early regime only certain portion of the solid is affected by the thermal disturbance at the boundary. So we took something like this. So this is T is equal to Ti throughout, and then we suddenly cool the sides, okay, heat treatment of a ball bearing, heat treatment of a helical coil spring or a carriage spring of your truck or helical coil spring of your car or whatever. If you do so that if you can if thermal conductivity is very high and if the Bayer number is much smaller compared to 1, you can use a lump capacitance system. That is one thing. If you cannot do that but you are still in the early portion of the cooling, then the center will not know that there is a disturbance, right. So the disturbance propagates from the end. So in the early regime we can do something called the similarity transformation. The whole idea of a similarity transformation is to convert the partial differential equation into an ordinary differential equation, and ODE is easier to solve. In the middle regime you have to use the full solution, and in the late regime you can use what is called the lumped capacitance system, where more or less the system is reaching the temperature of the surrounding, so you can lump the whole solid to be at one temperature. And so yesterday we saw the exponential temperature distribution, this, right. Even if you plot, lot of systems in real life follow this. Last 10 days if you plot the attendance in this course versus time, it will follow it is theta by theta is e to the power of minus t by tau, okay. So that is a law of nature that is exponentially decaying, okay, exponentially decays with time. So that is the solution for the lump capacitance system. Now in yesterday's class I looked at this, we looked at this early regime where we introduced a similarity variable called eta. Eta is x by 2 root alpha t. Temperature is a function of both x and t. Therefore if you introduce x by 2 root alpha t, it is an intelligent choice of 2 variables combined in such a way that when you work out, when you get when you try to use the similarity transformation, automatically the PDE is converted into an ODE. Yesterday some people had a doubt, there was no problem with this. D of temperature by D of time is dt by d eta, because temperature is a function of eta only, into d dou eta by dou t, this is like this. Now we got dt by dx the same, dt by d eta into dou eta by dou x. So dou eta by dou x is 1 by 2 root alpha t, that is given here. But when you are going to do dou square t by dou x, first you do dou by dou x of this. Once you do dou by dou x of this 1 by 2 root alpha t has got no business with x, so he can be pulled out. So you just pull out 1 by 2 root alpha t, then you have got dou by dou x of this. Dou by dou x of this is d by d eta of this and dou eta by dou x. Once you do that, then this alpha, all this get cancelled, then I again have that x by root alpha t, x by 2 root alpha t is eta, therefore x by root alpha t will be 2 eta. So d square t by d eta square plus 2 eta dt by d eta equal to 0. So this is a similarity, this is the ODE which you obtain by using the similarity transformation. The beauty of this is as follows: you can assume that let dt by d eta be equal to p, okay, then this will become dp by d eta plus 2 eta p equal to 0. So it will just become a first order equation, and apply the boundary conditions and you can solve it, and you will get what is called the error function. So it is a very simple way of solving a transient. So you have simplified the original partial differential equation because you exploited the concept of limited thermal disturbance in the initial portion of the cooling or heating, okay. The whole of the solid is not affected. Now if you look at the boundary conditions, let us take a solid like this, x is like this, so it is Ti, t equal to Ti, t less than equal to 0. Some people do not like less than equal to 0, right, okay. So this t equal to Ts, okay. So eta equal to 0, and eta tending to infinity. Eta tending to 0 means what? That means eta tending to infinity is x tending to infinity and t okay. See the beauty of this. Please look at the board. Eta tending to infinity means somewhere further. Assume that this is called a semi-infinite slab. That's why it's called a semi-infinite slab. At a given time, the penetration depth delta is much smaller compared to the L. That is why it is called semi-infinite in extent. This delta, the penetration thickness may be 5 mm, the slab may be 30 centimeters long. That means 29.5 centimeters of the slab does not know that there is a disturbance at the first 5 millimeters. Okay. Now eta tending to infinity, what is the story of eta tending to infinity? Is x tending to infinity. X tending to infinity, do you know the disturbance or not? At x tending to infinity, we do not know the disturbance. Therefore, what is the boundary condition for temperature? T equal to Ti. T equal to Ti is the boundary condition for eta tending to the infinity. But the beauty is T equal to Ti is also the initial condition. That corresponds to T equal to 0 everywhere. Therefore, by an intelligent choice of eta, you are able to absorb one boundary condition and one initial condition. That is why it beautifully reduces the partial differential equation into an ordinary differential. Because the original equation has to support 3 conditions, 2 boundary conditions on x and one initial condition on time, because you have dt by dt and dou square t by dou x square. Now it has become second order in eta. Therefore, it cannot support 3 conditions, but physically those 3 conditions are real for the problem. Therefore, this eta has absorbed 2 of these conditions into one condition on eta equal to infinity. Are you getting the point? So there is no degeneracy, there is no loss of information because we try to use this procedure. Is the funda clear? Okay, now we will solve a problem in the lumped capacitance method. Problem number 48. Very good. Stainless steel balls 10 millimeter in diameter. Stainless steel balls 10 millimeter in diameter are annealed, A-N-N-E-A-L-E-D, are annealed by heating to 1200 Kelvin. Stainless steel balls 10 millimeters in diameter are annealed by heating to 1200 Kelvin and then slow cooling to 375 Kelvin in air, and then slow cooling to 375 Kelvin in air. Okay, I am using telegraphic language. H equal to 25 watts per meter square Kelvin. If somebody is a purist, you will say the heat transfer coefficient and the interface, you can write all that. H equal to 25 watts per meter square per Kelvin and T infinity equal to 40 degrees centigrade. Properties of stainless steel are thermal conductivity 20 watt per meter per Kelvin, density 7900 kilogram per meter cube, Cp 477 joules per kilogram per Kelvin. What is the question? What is the question? What is the time required for the cooling? This is a question which can be answered only by the heat transfer engineer. Okay, what is the time required for cooling? Okay, ten millimeters phi, 10 millimeters in diameter. The first step in technology is bio number. First check whether bio number is all right. If characteristic length is not so apparent, take the ratio of the volume to area. Okay, 4 by 3 pi r cube. Similarly, you can work out for slab, cylinder, or even an arbitrary shape volume. Okay, so r by 3, r by 3, how much is it? 1.66. Correct. Now bio number, so the bio number is ridiculously small. For a ball bearing and all that, blindly you can start assuming it is a lump capacitance. Good thermal conductivity, very small size, good heat transfer coefficient. I mean, it should not be too good, then H is in the numerator, reasonable heat transfer coefficient. So, what is it? Bio number? 2 point? I will put 2.1 and 10 to the minus 3. So, I will write like this: bio number less than 0.1. Therefore, the lumped capacitance method is valid. Okay. So, time constant Umesh, finish. Okay. This is that's all, Is it correct? Yeah, I made some mistakes. What is it? How much is it? 251 point. Okay. What, Deepak? So, theta by theta I, theta it must get cooled to 375. 313 correct. 1200 minus so take ln both sides on the calculator, multiply by 251 and you will get some decent time. 700 seconds, 800 seconds, how much is it? 668. Okay. So after about 11 minutes or so, you can pull out the stainless steel ball bearing. It will come to this temperature. It's good. Okay. Suppose there is a radiative heat transfer. Even then, the lump capacitance system can be used, but you have to do the equivalent radiative heat transfer coefficient. Right? I have told you the linearization t to the power of 4 minus t infinity to the power of 4 is t square minus t infinity square into t square plus t infinity square. T square minus t infinity square is t minus t infinity t plus t infinity. Combine all the terms and call it as HR, radiative heat transfer coefficient, into t minus t infinity and add it. Suppose I give you a problem in which combined convection and radiation is there, the total heat transfer coefficient must respect the Biot number less than 0.1. Okay. Anyway, we leaving the mathematics apart. What is this time constant now? Time required for the temperature to drop to 66% of initial whatever, right? So theta by right when T is equal to tau 1 by E, correct? Did I make it? Did I mess it up or it's okay? 1 by E. Therefore, am I okay? Similarly, let us take T and okay. Suppose the doctor wants to get the fever temperature accurate to, let us say 0.2 is okay for him, 0.05, 0.05, 0.1 is too fine a number, they are not engineers, they can't handle such numbers. Okay. What is a good accuracy for a doctor? Less than 0.5. Okay. No, why I am doing this is, if it is less than 0.5, let us say somebody has a 0.5 centigrade or Fahrenheit? Fahrenheit. So we have to give some respect to doctor, man. So we will give 0.5 Fahrenheit, that is about 0.3 centigrade. Okay. So let us say that somebody has a fever of 40 is too much, 104. Let us say 39 is a decent fever. Okay. So so he wants accuracy is about 0.3. Okay. So if it reaches about 38.7 degrees centigrade, it is okay for him, he will live with that error. So if it is like this, so if the actual temperature is 39, so he wants to know at what time it will reach 38.7, that will be related to the time constant. Invariably the doctor pulls out at the end of 2 minutes. So correct, at the end of 2 minutes it that is directly related. You can find out the time constant of this mercury in glass thermometer and find out. Nowadays you got electronic this thing which which gives a beep. Okay. And but if you take you can fake a fever by going to Tiffany's, having a coffee and then going to the or you can take a Pepsi and the doctor will get scared, hypothermia. So or in Europe what they do is they insert the thermometer into the ear, the ear temperature, or they will measure the forehead temperature, because the core temperature inside is not actually known. These are all diagnostic of oral temperature is diagnostic of something happening inside, or you are using infrared thermograph or something. Okay. Ear thermometers are slowly getting popular here also, they are expensive. Okay. Fine. So this is the idea of how much time you want. So the time is related to the accuracy. Now what is this theta by theta I? Is it okay? What is alpha? Fourier number? What is it? What is the story now? Alpha what happened to the not by bio number, then there is a k, oh there is a k there, okay. Now what else is there? H rho Cp alpha is denominator, k by rho Cp, some L is there somewhere, man. What is HLC by k? What is this? So theta by theta I is e to the power of minus bio number into Fourier number. I am saved. That is the way it should be. If you recall, when we started the non-dimensionalization, I told you that theta is a function of xi, bio number and Fourier number. Xi gives this spatial variation of temperature, bio number gives the conduction convection coupling, and Fourier number gives the variation of temperature with respect to time. Now it is a lump capacitance system, therefore the spatial variation should go, therefore the dependence of theta on xi has vanished because it is lumped, therefore as it should be. See, if you are working on a project or a heat transfer problem or research or something, you have to just take a paper and pencil and keep on working. Before going to the computer, so much is possible. Okay, you can extract lot of information without actually solving the equation by non-dimensionalization, scaling analysis, and that is how you get the physics. Okay. Now let us go to the last part. I will look at the, I did not tell you the full solution. The full solution will be what I basically do is I assume that theta is a product of two solutions, x of x into t of t, where x is a function only of x and t is a function only of t. Now I take d theta by dt, d theta by dx, d square theta by dx squared, and then I will arrive at terms on the left side and right side. Left side will be a function only of time, right side will be a function only of x. If both have to be equal, both of them have to be individually equal to some constant, I call it as lambda square. Then I am essentially breaking down the PD into two ODEs. I solve this is called the superposition principle. I combine the solutions and using the boundary conditions I get ABCD. So if you do that, what you are essentially doing is called the method of separation of variables. I should not put method of separation of variables here because the separation of variables has not come here. In the next two steps it will come when you put d theta by dx and d theta by dt. Okay. So this is the full solution which is applicable for the middle regime as well as for the early regime and the late regime. However, for the early and late regime this complicated solution is not required. We can use the lump capacitance for the late regime and use the similarity variable for the early regime. Okay. And these have been solved and these are available, and these charts are also available. Standard heat transfer books and the so called data books will give you the various charts for theta as a function of xi, Biot number and Fourier number. So you have to calculate Biot number first, then Fourier number, and find out x by L, and for cylinder, sphere and the slab charts are available in several textbooks. You can use it, or you can program in MATLAB and get the solution right away. You can use MATLAB solution and use the PDE solver. Okay. Now the last part is we look at the Laplace equation. So if I have a lump capacitance with heat generation, so it will be that is I have a dipper heater, okay, immersion heater. Initially it will rise, then the temperature becomes so high that the losses will be equal to Q, then this will vanish, then Q will be equal to Hi into T minus T infinity, you will get the steady state temperature. Then if you switch off, or you can have a situation where okay. So one good example would be basically I am cooling some electronics in a spacecraft, and then I am using a fluid, an organic fluid, to cool it. Then the fluid gets hot. That hot fluid has to be cooled again so that it can continue the cooling process. Therefore I can have a glass, I can have a device which is made of glass like this. Then I can have an atomizer, a pump which just sprays these particles, oil particles. The oil particles move with a velocity. Now each of these can be considered to be spatially isothermal, and then if you know all the properties, and now if the ambient is just outer space at 3 Kelvin, the cooling will be accomplished. So the design will be, what should be the length, if I know what is the velocity with which I push this drops out, what should be the length of this device such that by the time it comes out, so if it enters at 60, I want it back at 35 degrees centigrade. So this is called a LDR, a liquid droplet radiator. So even the lump capacitance system looks so simple, but it has got so many applications. So Vinay, you didn't get it? Huh? Yeah. So the governing equation will be this. There will be a lot of fun because dt will be taken to this side. Then you have to use the method of partial fractions. Tan inverse of ln of, all this will come. Okay. I can just give you a 15-minute course on finite differences. Finite differences can be taught for 40 hours. Okay. So let us consider the simple Laplace equation, which is del square t equal to 0. This can be derived from the general equation. So if you had the heat generation term, it is called the Poisson equation. Okay. Let us consider the situation. You remember when I started discussing the Fourier's law, this figure I used to discuss heat flux lines and isotherm. This is the 100-degree isotherm, this is the 0-degree isotherm, all the other isotherms will be like this. Is it okay? Now this can be solved using the method of separation of variables, but how do you solve it using finite difference? Let us take a square slab L. So what I do is I take a particular node called I comma j, then I take one more node I plus 1 j, I take here I minus 1 j, I take here I j plus 1, I take here I j minus 1. Okay. Now what I do is I can calculate dt by dx at I plus half comma j, that is here in the middle. The temperature gradient here using a Taylor series approximation retaining only the linear terms will be T of the node ahead it minus the T of node behind it divided by the delta x. That is a finite difference approximation. So I am replacing it, replacing dou t by del t and replacing dou x by del x. This will just be assuming that all the delta x's are same, otherwise I have to put xi plus 1 minus xi. Okay. Similarly, dou t by I can take the derivative here, that will be t so this will be T I of j minus, so what I am essentially doing is called the forward difference. Is it forward difference? I am doing central difference, okay. Here I am doing central difference. Now I will say what is d square t by dx square at ij is nothing but dt by dx at I plus half j minus dt by dx at I minus half j divided by delta x, very good, because this is nothing but dou by dou x of dt by dx. What is this? Okay, use that. Therefore I got a central difference approximation for the second derivative. Similarly, T I j plus 1 you can make delta x different from delta y, but the simplest case will be delta x equal to delta y. Why are we doing all this? We want to get an expression for Tij in terms of its neighbors. What is the fun in doing this? This I can vary from 2 to n minus 1, the j can vary from 2 to m minus 1 if it is a non-uniform grid. Then each of the Tij's is related to its 4 neighboring nodes. Then when you do this at I, for I equal to 1 and I equal to n, for j equal to 1 and j equal to m, the boundary conditions are given to the problem, the 4 boundary conditions are given. So the boundary conditions will start feeding and you can solve the system of simultaneous equations for Tij's either using matrix inversion or Gauss-Jordan elimination or Gaussian elimination or Gauss-Seidel method. All the CFD software work on essentially this. Finally you get a system of simultaneous equations for a particular node Tij. Instead of Tij you can have Uij, U velocity, Vij, rho ij for the density or concentration and all that. However, it will not be the diffusion equation. Apart from diffusion you will have the convection or the advection terms U dou E by dou x plus V dou E by dou y and so on. Okay. This is essentially numerical heat transfer. Therefore, Tij equal to Ti plus 1j plus Ti minus 1j plus Tij minus 1 plus Tij plus 1 divided by 4. So this is called finite difference method. Okay. Please look at the board. I can derive the same equation in a slightly different fashion. I can derive the same equation in slightly different. Please look at the board. I can take half so my control volume is delta x by 2 into delta y by 2. I can find out what is the q which is entering here, what is the q which is leaving here, what is the q which is entering here, what is the q. The net will be k into T of this minus T of this divided by del x square. I can replace the Fourier's law by just using finite differences. I can do an energy balance. So this is called a control volume formulation. If you take delta x equal to delta y and it will result in the same equation. Okay, you can do a flux balance. The net flux which is coming will be equal to 0. Actually when you say that the net flux is equal to 0, you are actually integrating the governing equation once. So essentially what I am using is the integral formulation of the governing equation. So the finite difference uses the differential formulation. The finite volume and the finite element method will integrate the governing equation. Integrate means what? We are across a volume we are finding what is the story. Okay. Anyway, let us not get into that, we will get buried deeply. If I have 1 more hour I can derive it, I will derive it for the Poisson equation, but now there is no time. So the basic story is the nodal value for a diffusion equation is east plus west plus north plus south divided by 4. The divided by 4 comes because you get 25% weightage to all this. Otherwise when you write your CFD software it is always like this. Always in life there are 4 people. Okay, they always talk about 4 people, if 4 people are happy you can do anything. I mean such type of stories are also there. Eventually also some 4 people are required. Okay, so here also there are 4 neighbors. Here also there are 4 neighbors. So the value of the function at a point is a weighted average of its neighbors. If all the neighbors are at equal distance, we give 25% weightage to each of them. If they are at different distance, it will be W east into value at east plus W west into value at west. The sum of all the W's will be equal to 1. That is the weighted this is a weighted mean. So this is essentially the diffusion. You can put the convection advection also. Now what will a mathematician do? This everybody knows what is this. So what he will do is, so what will be a quick answer to this problem? 100, 0, 0, 0. If it is a very crude method, what will be the center temperature according to the algorithm? 25. So this is the first program, whoever wants to do BTP with me, this will be the first program I ask them to do. Solve it using finite difference and prove that the center temperature is 25. You have to change the number of grids. So the center temperature will approach either like this or it will approach like this. Okay, this will be number of nodes. When it has reached somewhere, then you say it is grid independent. Okay, these are all part of a numerical study, of any numerical study. So what I have done essentially is called what is called a 5-point stencil. In computational heat transfer or CFD, they will say it is a 5-point stencil. That means the value of the node is dependent on 4 neighbors. That node itself plus 4 others is called a 5-point stencil. You can have a higher order scheme. I don't know, you can call it east. You include these fellows also. What stencil is it? 9-point stencil. They have 13-point stencil, 21-point stencil. Then they have a stencil which is equal to the number of grids. I have reviewed papers for high class journals because, and they will prove that compared to 2-point stencil they are able to get with much less grids, they are able to get accuracy, blah blah blah, all that, right. So are you getting the point? When will you get the 9-point stencil? In the Taylor series you stop with linear, then you go to the second order terms, you go to the third order terms, then you will get higher order stencil. Delta x need not be equal to delta y, then the average will not be it won't be 25%, 25%, 25%. Okay. Now if you have, once you write for P, you can similarly write for E, you can write for N, you can write for this, and then what you do is basically suppose I give you a problem, I give you the grid pattern. Suppose in the exam I ask you a question like this, there is a square slab 10 centimeters long and 10 centimeters wide and one unit depth the direction perpendicular to the plane of the board. The various boundary conditions are given, there is no heat generation, constant thermal conductivity, steady state, blah blah blah. Then using any iterative technique, using a central difference approximation, get the temperatures T1, T2, T3, T4 to a reasonable accuracy. Problem will go like this. How do we solve this problem? I will write the finite difference for T1 first. T1 is west, east plus west plus north plus south, right. So 50 plus 100 plus T2 plus T4 by 4, okay. T2 equal to 100 plus 50 plus T1 plus T3 by 4, T4 equal to 50 plus 50 plus what T1 plus T3 by 4, T3 equal to T2 plus T4 plus 50 how do you start the operations? Let T1 equal to T2 equal to T3 equal to T4 is equal to 70 degrees centigrade, first iteration, okay. Once it is 70, I will come to first T1, okay. 70 plus 70 plus 100 plus 50 by 4, I already have T1. Now watch carefully, Now T2, T3, T4 are 70, but T1 is calculated. So when I go to T2, I use the latest update of T1. So that if I do that, that is called the Gauss-Seidel method. It has to satisfy diagonal dominance and all that. Fortunately, it automatically satisfies. You don't have to worry about this here. Then you will get T1 and T2, get the latest updates, and at the end of the first iteration, compared to your original 60 degrees assumption, find out how much T1, T2, T3, T4 have changed. So you can put a criterion as sigma okay. This is called the norm, R squared norm. You can put a norm, that is T1 previous iteration minus old iteration square plus T2 old previous this iteration minus whole square, and then this R squared must reach a reasonable value, 10 to the power of minus 4, 10 to the power of minus 5. Very easily you can implement it on the computer. If it is on the computer, why use only 4 points? I can use 400 points. But whether 400 points are required or not, if you are trying to establish that, then you are trying to establish what is called grid dependence or grid independence. The solution is independent of the grid pattern. The solution has converged, but the solution may also converge to a wrong answer. Therefore, apart from grid independence, you have to validate. In this case, you know center temperature 25 is a validation. For certain other problems, when you are in the wilderness, then you have to take recourse to literature. If somebody already has an analytical solution or somebody has an experimental result, then you validate. That cannot be a research problem because already somebody has done. Now you say that he did only this much, now I am considering some more, and then you proceed with your work. Okay, we can keep on going like this. We can write down the finite difference algorithm for the Poisson equation, and when you start writing the finite difference for cylindrical and spherical coordinates, it will become very, very interesting. Okay.